Hello, this is Mr. Henry, and welcome to Lesson 3.6, Similar Figures in the Real World. The central question says, how do I use similar properties of similar figures to solve real-world problems? And the warm-up here is just asking, in your opinion, what makes solving real-world problems harder? We've talked about this before, and I think for the most part, people, the difficult parts about a real-world problem is understanding what the question is asking, or being able to recognize and understand the whole scenario. And I think it comes down to reading ability has a large part of it, but also the background knowledge and understanding and imagining, picturing in your head exactly what's happening in the word problem. So my typical solution is, if you have a hard time imagining everything going on in your head, draw a picture. You see me draw a picture of almost every single problem, and that's going to continue. And I do very well at my word problems. So the first one here is vocabulary. These are the same vocab as the last lesson. Similar figures are two shapes that are proportional in size, and corresponding parts are the same parts but the other picture. So nothing new there. This lesson is devoted to just these real-world problems. So the first one here says, a Matchbox car has a scale of 1 to 64, meaning for every 1 inch on the toy car is 64 inches for the real car. Dale measured the side view mirror of his car and found it is 10 inches. How big would the side view mirror of the toy car be? So, since these are scale models of each other, they are similar. This scale is like the scale factor of our dilations. That's telling you how to get from one to the other, from the fake thing to the real thing. So I'm going to use that as part of my proportion. 1 over 64. This is the fake number, the fake length like the drawing or the picture or the model, and the bottom number is the real thing, like the real car. So it says Dale measured the side view mirror of his car and found it is 10 inches. Now that's his real car. How big would the side view mirror of the toy car be? Well, there we go. Now this is relating, again, toy car to toy car, real car to real car. 1 inch on the toy car relates to 64 of the real. X on the toy car is 10 on the real. So if we cross multiply this, we get ourselves an answer. 10 times 1 is 10. 64 times x is 64x. Divide both sides by 64. And we get, Mr. Calculator, 10 divide 64 equals 0.15625. 0.15625 inches equals x. So that's small. We're talking less than a quarter of an inch. And it makes sense. If you ever look at a Matchbox car, that side view mirror is pretty tiny. It's about 0.15 inches. So scale models, scale drawings, that scale is like your ratio. It's your scale that relates the fake thing to the real thing, and you can use that to help you with your similar figures. Letter B. Larry is carving an ice swan for a wedding. His model is 1/6 the size of the actual carving. If his model weighs 3 pounds, how much will the actual carving weigh? Go ahead and pause the video and try this one on your own. Alright, so he has his 2 swans, and there's my beautiful swan. There's one swan, and he has another swan. Nice. So his fake swan is 1/6 the size of the real. So the fake is 1/6 the size of the real. That's what it says. His model is 1/6 the size of the actual carving. So I'm using this as my fake, the model, and this is the real deal. So it says if the model weighs 3 pounds, this fake one weighs 3 pounds, how much will the actual carving weigh? Now these are similar figures. There should be similar shapes. But the first thing that I think about, because I wrote this out just kind of modeling what it says here, but to me this is just an equation. The fake thing is 3 pounds. And 1/6 of the real, I'll use an R. If I would solve this equation, times both sides by 6, the 1/6 and the 6 cancel because they're reciprocals of each other, and that gives you 18. So the real thing would be 18 pounds. Now this is not the only way to do the problem, but that's the way that just appeared at the top of my head as I was thinking about this. But we could also use a proportion. The 1/6 here is also kind of like our scale factor. And so if we take our scale factor, and this would be the fake to real, well, the fake weight of this swan is 3 pounds. The real weight, we need to figure out. And if we cross multiply this, because they are similar, 1 times x is 1x, 6 times 3 is 18, and we get x equals 18 again. So it's still 18 pounds. So in that case, drawing the picture might have been helpful. Labeling some stuff might have been helpful. Modeling out the little equation, it says her model or his model is 1/6 the size of the actual carving. That helped me out a ton. Letter C. Tom is given 3 cereal boxes as shown below. There they are. Alright. He needs to determine which 2 are similar. Alright. So which 2 boxes are similar? And, so, question number 1. And what is the difference in the volume of the larger box to the smaller box? So there's 2 different parts I have to do here. I have to find which 2 are similar, and then find the difference of their volumes. So to find the difference of the volumes, difference means subtract. So I'm going to have to subtract the volume of the bigger box to the little box. So volume of the big minus the volume of the small will give me my difference. That means that after I find which 2 are similar, I have to go through and find their volumes. And luckily for us, it gives us a volume formula. Use volume equals length times width times height to find the volume of the rectangular prism, where L is the length, W is the width, and H is the height. So the first step of this process, to me, would be find which 2 are similar, then I find their volumes, then I subtract their volumes, and I get my answers. So, similar figures. I've got 3 boxes, and so for me to tell which 3 are similar, I'm going to do kind of like I did in the last lesson, or the lesson before that, I don't remember anymore, where we had like 3 triangles and we're trying to find which 2 are similar. If they're similar, their sizes would be proportional. So I'm going to start with comparing A and B. If that doesn't work, then I go A and C, and then I do B and C. Okay, so here we go. I'm going to start with A and B. So if they are similar, they would be proportional. So I'm going to pick a couple sides. I'm going to pick this side, which corresponds to that. So 12 corresponds to 6, and 3 corresponds to 1.5. If I cross multiply, 3 times 6 is 18, 1.5 times by 12. Clear. 1.5 times by 12 is 18. Look at that. First try, I found which two are similar. So boxes A and B are similar. So first part of the question, which boxes are similar? Box A and box B are similar. There we go. So first part of the problem, done. I didn't even have to check the other two because those two were similar. Now, I can tell you if you check the other two pairs, they're not going to work out. So now I'm on to the second part of the question. I need to find what is the difference in the volume of the larger box to the smaller box. So I need to find the volumes of these boxes. So I need to find the volume of the big box and the volume of the small box. So volume of the big would be length times width times height. And what are the length and width and height of the bigger box? Well, if I'm looking at A and B, I don't even need him anymore. So the bigger box, it definitely looks like A. All the sizes are bigger. So the length, well, honestly, it doesn't matter what you use for length and width and height for a rectangular prism. So I'm going to use a length as 3, width is 8, height is 12. Pop those babies into a calculator. 3 times 8 times 12 equals 288. And that is the volume of the big. Alright, so I know now that the volume of the big rectangle I just recopied this line down here because I'm going to start plugging stuff in. The volume of the big is 288. Alright, what's the volume of the small rectangle? So that would be these three. So still length times width times height. Always write down your formula when you're using a formula. 1.5 times by 4 times by 6. Alright, and Mr. Calculator says 4 times 6 times 1.5 equals 36. So I can plug that back into my formula here. Oh well, he's attached. And what we find here is that if I go through and I do my math, volume of the big minus the volume of the small gives me something for an answer. I don't know. 288 minus 36. 288 minus 36 equals 252 inches cubed. I forgot to put my labels. These are inches cubed. Inches cubed. So let's see what we have here. Which boxes are similar? I have boxes A and B are similar. Alright, check. What is the difference in the volume of the larger box to the smaller box? The difference is found by subtracting the two. So I subtracted the volume of the larger one, which I found here, minus the volume of the smaller one, which I found down here. And when I subtracted them, I found the difference is 252 inches cubed. So that problem was hard, especially if you didn't understand what was going on. But once I started breaking it down and figuring out what I need to find, okay, how do I find that thing? Knowing that the difference is made by subtracting the volume of the big one and the volume of the small one, told me that someplace throughout the problem, I'm going to have to find the volume of the big box and the volume of the small box. So once I found which two were similar, that was my next task. The volume of the big one, do it. The volume of the small one, do it. Plug them in, and I get my answer. Letter D. It says, Brittany is 5 feet tall and casts a shadow, a 3.5-foot shadow, at 10 a.m. At that time, a nearby tree casts a shadow, 17-foot shadow. 2 hours later, Brittany's shadow is 2 feet long. What is the ratio of Brittany's height to the tree's height? Go ahead and pause the video and try it on your own. I would highly recommend you draw a picture. Okay, here we go. So Brittany is standing here. It says she is 5 feet tall and her shadow is 3.5 feet. At the same time, a nearby tree, ain't it beautiful, casts a 17-foot long shadow. Alright. 2 hours later, Brittany, who would still be 5 feet tall, casts a shadow that's only 2 feet long. What is the ratio of Brittany's height to the tree's height? Okay. So, actually I guess it'd be 12 p.m. We need to find the ratio of Brittany's height to the tree's height. In order to write a ratio, we need to know both pieces. We need to know the ratio of Brittany's height over the tree's height. If we can plug in a number here, which is 5, that's Brittany's height, she's 5 feet tall, and a number here, we would have our ratio. If the tree, play pretend here, don't write it down, if the tree was, say, 8 feet tall, then the ratio would be 5 over 8. Now, the tree's not 8 feet tall. We have to find how tall this tree is. So we're going to use all this other information they gave us to find the height of the tree, because that's what would give us our final answer, the ratio of Brittany's height to the tree's height. Alright, so looking at this other information I have here, what can help me find how tall the tree is? Well, if you remember a previous problem about something casting shadows, how it makes similar figures, because this angle would be the same, and that's a right angle, and this angle would be the same, and that's a right angle. These are two similar figures, triangles. And since they're similar triangles, we can use a proportion. Let's see what we got. We're trying to find this, the height of the tree. So 5 corresponds to x. 5 corresponds to x. 3.5 corresponds to 17. 3.5 corresponds to 17. If we cross multiply, we find out what x is. So we get 3. I'm going to change the 3.5 to a decimal. It's going to make it easier. 3.5x equals 85. That's 50 and 35. 5 times 17. And then we're going to divide both sides by 3.5. We're getting the variable by itself. X equals 85 divided by 3.5 equals 24. We'll call it 24.3 feet. So we found what x is. X is the height of the tree. That tree height is the thingy we needed in order to write the ratio. That was our whole goal. We wanted to write the ratio of Brittany's height to the tree's height. In order to write the ratio, we needed to know how tall the tree was. So that's why we did all this other stuff. So the ratio is 5 to 24.3. That's my ratio. This other extra information about at 2 hours later, her shadow is only 2 feet long, that's just extra information, just trying to throw you off the trail a little bit. It wasn't needed. It wasn't essential to solving the problem. Alright, so the problem here, letter E, says the front yard and the backyard of the Joneses' home are similar rectangles. So I'm going to draw a picture. So there's our roof of our house. We've got 2 yards, front yard, backyard. Alright, the backyard is 20 feet by 30 feet. 20 by 30, so there's the back. The front yard, the longer dimension of the front yard is 20 feet. That's the longer side of the front yard. What is the combined area of the Joneses' yard? So a combined area, to me, means we're going to take the area of the front plus the area of the back to get their total yard. That is our goal. That's what we want to do in this problem. Now, what stuff do we know about? Well, I can find the area of this backyard. This backyard is a rectangle. See? Rectangle. And the area of a rectangle is found by doing length times width. So 20 times 30 gives me an area of 600 feet squared. So right now, I can automatically plug that into my formula. My backyard here is 600 feet squared. I don't want that label in there. Too big. 600 feet. All right. So now I need to figure out what is the area of the front yard. All right. To find the area of the front yard, I need length times width. I have my length. What I don't have is I don't have this other dimension, the shorter side of the front yard. I'll call it X. So that is really what this problem comes down to. If I can find this side, I can plug it in for my width. Then I can find the area of the front. And I can plug that in here. Then I can find the total area of the whole yard. So that one piece is where this entire problem comes together. So, how do we find this side? Do you remember how I said that there are similar rectangles? How do you find the missing side of a similar figure? You use a proportion. So we proportion this thing. 20 corresponds to X. 30 corresponds to 20. And I cross multiply. 400 equals 30x. Divide by 30, divide by 30. And these cancel. I get x equals 400 divided by 30. 13.3 feet. So now I have that last piece of information that I can plug in that's going to go and finish up my problem for me. This piece is 13.3 feet. So the width of the yard, 13.3. I can now find the area of the front. 20 times 13.3. 266. I can now plug that in here. 266 is the area of the front. And now That allows me to find the total area of the front yard. 266 plus 600, I didn't need a calculator, but I pulled it up. 866 feet squared. What is the combined area of the Joneses' yard? That's the front and the back together. So I found the area of the front, the area of the back. The area of the back was simple because it gave me all the dimensions I needed. The area of the front, I had to find my missing piece. Because the shapes were similar, I can use a proportion. And so I set up my proportion, I cross-multiplied. The missing piece was 13 feet. That allowed me to plug it back into the formula for the area down here. 20 times by the 13.3 was 266. And that 266 was what I needed for my final answer formula here. And I got an answer. 866 feet squared. That is the area of the Joneses' yard. Letter F. Ralph's Pizza Shop sells two sizes of rectangular pizzas that are similar in shape. A large pizza is 12 inches by 18 inches. The shorter side of the small pizza is 6 inches. What is the perimeter of the small pizza? If you could please, pause the video right now, try the problem on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so picture time. We need two pizzas, rectangular pizzas. So there is one, there is another, and let's throw some pepperonis on there for good measure. Love them. Alright, so we've got our two pizzas. This large pizza, it says, is 12 inches by 18 inches. The shorter side of the small pizza is 6. So here's my small pizza. The shorter side is 6 inches. What is the perimeter of the small pizza? So the final question is asking for perimeter. The way you find perimeter of a rectangle, the perimeter is you take all of the sides and you add it together. So this is 6 inches. The bottom would be 6 inches. I don't know this side here. It's not given to me in the problem, so I'm going to call it x. And this other side would also be x. So my perimeter would be 6 plus x plus x. If I can find out what this x is, this one missing side, I can find the perimeter, and I'm done. So let's do that. These two shapes are similar. It said so in the problem. Similar shapes, you can find a missing piece using a proportion. So 12 corresponds to 6. 18 corresponds to the x. Cross multiply this thing, we get 12x equals 60 and 48, that's the 108. Divide by 12 on both sides. We're solving this equation. X equals 9. So my x, I can erase it now in the problem, boom, boom, is 9 inches. That's the piece I needed to plug in here. My x is 9 inches. So my formula comes from perimeter is 6 plus 9 plus 9. The perimeter of my small pizza, 6 plus 9 plus 9. I'm adding them all together. Let's see, 12 plus 18. Perimeter is 12 and 18 is 30 inches. And that is the perimeter of the smaller pizza. So I had to find the perimeter of the small pizza. That was what the question asks. I put down what I need to do to find perimeter. Perimeter is you add all of the sides of the small pizza. I knew the top and the bottom were 6. It said so in the problem. I did not know the left and the right, this long side of the pizza. So my goal was, if I can find the long side of the pizza, I can then find the perimeter. I knew that the two rectangles were similar, so I used a proportion. I cross-multiplied and found the side of the pizza is 9. Therefore, I plug it back into the formula, and 6 plus 6 plus 9 plus 9 gives me 30 inches. That is my perimeter. Last problem. Letter G. A rectangular goat pen has a perimeter of 20 meters, and its area is 24 square meters. Kevin is planning on building a larger, similar-shaped pen. He wants the longest side of his new pen to be 10 meters. What would the perimeter and area, or what would be the perimeter and area of the new pen? So, this is a DOK3, which means it's going to take some time, it's going to take some effort, it's going to take some space. Pause the video, try it on your own. When you're ready to continue, hit play, and we'll go through it together. Alright, so let's see what we got. A rectangular goat pen has a perimeter of 20 meters and an area of 24. So, rectangle, perimeter is 20, area is 24. He's planning on building a larger pen, and he wants the longest side of his new pen to be 10 meters. Alright. What would be the perimeter and area of his new pen? Now, in order to find area, I need to know let's do these over here. Perimeter and area. In order to find the area, I need the length times the width. For my new pen here, I know one of the sides, the length, is 10. I do not know the width. I need to know how wide this pen will be. For the perimeter, you're going to take and add all the sides together. So I'm going to take the perimeter is 10 plus 10 plus, and I'll keep using this W. This will be the width. W plus W. So if I can find the width here, that answers all my questions. So my goal is to find out what is this width. Okay. So the two shapes are similar, which means I should be able to use a proportion. The problem here, and the reason why this is a DOK3, is it does not tell me what the size of the sides are. It doesn't say they're 8 meters and 3 meters. I have to figure this out. Okay, so let's see here. In order for me to get a perimeter of 20 and an area of 24, perimeter of 20, area of 24, the only ways I'm going to get that area is from using this length times width. So what numbers multiply together to get 24? Well, I've got 1 times 24, I've got 2 times 12, 3 times 8, 4 times 6. So it has to be one of these 4. Now I just got to figure out which of these dimensions gives me a perimeter of 20. So let's see. If I have a rectangle that is 1 by 24, that would have a perimeter of 24 plus 1 is 25, and 25 would be 50. That's too big. The second one would be 12 and 2. That's a perimeter of 12 and 2 is 14, and another 12 and 2 is another 14 is 28. That's closer, but not good enough yet. I'm a little cramped for space. 3 and 8. So 8 and 3, 8 and 3. 8 plus 3 is 11. And another 8, another 3 is another 11. That gives me 22. Still not there yet. 6 and 4. 4 and 6, or the other way around. 4 and 6. So 4 plus 6 is 10. 4 plus 6 is another 10. 10 plus 10 is 20. There we go. I found which dimensions give me a perimeter of 24, a perimeter of 20 and an area of 24. This rectangle has to be a 6 by 4. So the long side, we said this is the long side would be 6, the short side would be 4. Now that we know this, we can do the rest of our problem. Now we know that we have to use a proportion because these two rectangles are similar. So 6 corresponds to 10, 4 corresponds to W. Cross multiply, 6W, 40. Divide both sides by 6. W equals, Mr. Calculator says, 6.6. So the width of my new pen, or of Kevin's new pen, would be 6.6 meters. That's the information I needed to actually answer the question. I haven't answered the question. The question was, what is the perimeter and area of the new pen? But now I can figure it out. The area, I'm going to plug in 6.6 for the width. So 10 times 6.6, it's going to be 66 meters squared. There's one answer. The perimeter, if I plug in 6.6 for the width, so 10 plus 10 plus 6.6 plus another 6.6, gives me a perimeter of, let's calculator this thing, 6.6 plus 6.6 plus 10 plus 10 equals 33.2 meters. So, what would be the perimeter and area of the new pen? The perimeter would be 33.2 meters, and the area would be 66 meters squared. Summary question says, how do you use similar figures to help you solve real-world problems? Go ahead and just jot down some notes, an idea or so. Pause the video, and when you're ready to continue, hit play, and we'll go through it together. Alright, so I have here, anytime you have similar figures, you can use proportions to help you find missing side lengths. And that's what we did, I think, in every single one of these problems. We recognized that the figures were similar. We figured out how to use these proportions to find the missing length. And most of these problems, or some of the problems, after we found the missing length, we might have had to do something else with it, like use it to find the area or perimeter. But that's what we did. We used proportions to solve the similar figures and find out what those missing lengths were. This has been lesson 3.6. Thank you for watching.